Yes. The next report we did with my colleagues from Kyiv State Universitet Oksana Sitnikova and Kharkiv National University of International Affairs, Kharkiv, and Victoria Rov, Kharkiv, Tatiana Kolesnik and Victoria Rov, Kharkiv National University of Internal Affairs. Topics the report: intelligent extraction of the informative features for UAV motion modeling, principles and techniques. The use of unmanned aerial vehicles is becoming increasingly relevant in various fields of activity. Some of the main reasons why UAVs are becoming more popular include: it is economic benefits. UAVs can significantly reduce the cost of performing various tasks. It is increased safety. UAVs can be used to perform tasks in dangerous or hard-to-reach places, such as disaster zones, forest fires, or search and rescue areas. It is increased efficiency. UAVs can accelerate task completion, reduce the time needed to obtain results, and improve data accuracy. It is real-time data collection capability. UAVs can be used for real-time data collection, allowing for quick responses to changing situations and effective decision-making. It is innovation. UAVs are a new technology that is constantly evolving and improving. The military sphere, the UAVs can use in reconnaissance and surveillance, in attack, in reduce personal risk, in communication, in training. Thus, the use of UAVs has a number of advantages and various fields of activity and is an actual direction in the development of technologies. It is known that one of the main control systems of the UAV is the autopilot. This figure in the slide shows the components for the UAV autopilot. Although that specific equipment shown in figure is used for a small low-cost UAV, it shares the some components found
Sorry, Sergey.
larger.
You don't change your slides.
Sorry. And now.
Yeah, maybe it might be better if you run present.
Okay, I open next. It is UV autopilot components. Yes.
Yep.
Yeah. Thank you very much. This figure shows the components for the UV's autopilot. Although the specific equipment shows in figure is used for a small low-cost UAV, it shares the some components found in larger and more expensive UAVs. For example, more expensive UAVs might have more powerful processing units or satellite communication links. Next slide. Can you see? And next slide shows the UAV autopilot components in a data flow diagram. In this diagram, the components of the autopilot can be divided into three major parts with make up the GNS, widens navigation and control. In this figure, the components marked in blue represents the communication and in and out of the UAV. The component marked in yellow represents the new ADSB communication, and the component marked in purple represents the sensors that can aid the guidance of the UAV. I would like to draw your attention to the elements highlighted in yellow. This is a model technology for information exchange between aircraft, which allows you to inform about the location of the UAV. We have determined route studying the data flow in the autopilot, several general cyber attack feasibilities. These attacks have been categorized into three groups: hardware attack, virus attack, and sensor spoofing. We have future identified specific attack scenarios which show the vulnerabilities of the current autopilot system. Looking at this from the cybersecurity perspective, it was natural to future categorize the attack into the following two types. It is control system security and application logic security. And next, the first question who we can use, who we can decide in our work, it is question modeling question and prototype work in modeling. Under the condition of increased requirements to accuracy and safety, UAVs in performing their task, a number of tasks of intellectual support of the control and life support system arise. Among such tasks, we can single out intelligent planning of the UAV flight trajectory under the influence of external factors. The goal of intelligent UAV flight path planning under the influence of external factors is to develop effective algorithms and strategies that will allow the UAV to adapt to changing conditions and ensure the accuracy and safety of its flight. Among the main tasks of intelligent UAV flight path planning, we can highlight the task of modeling the motion along the selected path. This task has found wide application in missions of automatic and semi-automatic following to a given point. I recommend optically taking into account external factors and influence its. In the context of intelligent UAV flight planning and the trajectory construction task, the main goal of the mathematical formalization stage is to ensure occurrence and consequently safe movement along a given trajectory. To achieve this goal, it is proposed to use variation autoencoders. And autoencoders is a natural network capable of learning the international representation of data and extraction its most informative features from the existing set. In the development model, a variable autoencoder can be used to reduce the dimensionality and reconstruction of the input data. This reduces the number of features and highlights important aspects of the data. The first step of data preparation for the variation of the encoders is date normalization. For this purpose, let's us identify the main parameters describing the position of the UAV in space and affecting the accuracy of its movement when performing a flight task. As parameters describing the position of the UAV in space, we will emphasize the following: L logistic range, H height, V velocity vector models, Q velocity vector inclination angle, and hiding angle, and that lateral displacement and accordance with the characteristics of normal Earth coordinate system. Some work authors give examples of converting the normal Earth coordinate systems to the trajectory coordinate system. The trajectory coordinate system you can see in this slide. It is okay. Using the result, some authors with the rotation and transition matrix from the normal coordinate system to the trajectory coordinate system are described as form a basic of transition vector of the trajectory coordinate system to the normal coordinate system. The rotation matrices are of the form number 1. The transition matrix from the normal coordinate system to the trajectory coordinate system has the form number 2. The basic of transition vector of the trajectory coordinate system to the normal coordinate system has the form number 3. Accordingly, we have form number 4. Using the basic of vector 3 and expression 4, we can determine the characteristic of the UAV motion as a material point. It should be noted that it's determined by its kinematics characteristics such as position, velocity, and acceleration. The position of material point is defined in three-dimensional space using coordinately x, y, z, which indicate its location relative to some reference frame. The velocity of a material point is defined as the change in its position with time. It can be represented by a vector that indicates the direction and velocity of motion. The acceleration of a material point is the change in its velocity with time. It can also be represented by a vector indicating the direction and magnitude of acceleration. Coordinates of the UAV velocity vector in the normal system we can see from formula number 5. The acceleration of the material point in the time differential of vector 5 we can see in formula 6. The motion of the UAV as a material point is determined by its initial state and the sum of external force represented by the coordinates f, x, y, and z, and the normal Earth coordinate system. If the vector f is decomposed in the trajectory coordinate system, be obtained in system f. According to Newton's second law, we can form a system of equation that determines the position of the material point in three-dimensional space 7. One of the most computationally difficult tasks is to take into account external influencing factors. Among such external factors, we can single out the force of gravity. This characteristic is not controllable. The other forces' action on the UAV can be considered controllable and can be represented as formal 8. We decompose the force vector into two components: the longitudinal load vector protection on the OX and the transverse load vector and Y protection on the OXY. A vector in the trajectory coordinate system using control parameters can be written as follows: 8 in taking into account the representation of forces acting on the UAV throughout hourlars and adding 3 differential equation relating the velocity vector to spatial coordinates. We obtain the following system of 6 differential equation describing the motion of the UAV, how 9 Formula 9, as can be seen from the system of equation 9. The control characteristics are not affine. They are not linear over the controls. At the same time, in order to normalize it and use it as input date in the variational autoencoder, it is necessary to transform it into an affine system. The conducted researchers have shown that for solving this problem in practice, and is possible to use rotation, stretching, compression, and shear method. Using the rotation method and considering the variables as new virtual controls, the following relation can be obtained of formula number 10. Considering the factors given in model, we present the input data set of the variation autoencoder in the form of table. Next slide. It is variational autoencoder input data set LH. It is variational autoencoder input data set VQ. It is variational autoencoder input data set next E and variational autoencoder input data set NX and Y. Three dense layers are proposed to solve the problem in this paper. After each layer, activation must be added to the encoder to introduce nonlinearity into the model. The activation function adds nonlinearity to the model and allows the neural network to learn complex dependencies in the data. In this paper, we propose to use the well-known activation function rectilinear unit. The layer of mean values has a dimension corresponding to the number of latent variables. The paper proposed to create a layer of dimensionally free. The variance logarithm layer should also have a dimensionally corresponding to the number of latent variables. The output layer of the encoder is a layer that predicts the parameters of the distribution in the latent space. In the case of these characteristics usually means predicted the mean and logarithmic standard deviation for each dimension of the latent space. The encoder output layers in our task will generate the parameters of the probability distribution of the latent space, which will be used to future sample to the latent representation and generate output date. In conclusion, we can see that the use of UAV in the intelligent interaction of information, future of UAV machine modeling, and in UAV trajectory modeling has the potential to significantly improve the efficiency and accuracy of UAV flight planning and control process. The VIE is capable of finding hidden differences and structures in the input data. As a result of the study, informative features that characterize the UAV motion are automatically expanded and presented in a reduced but still meaningful format. Using the intelligent system, the dimensionality of the data has been reduced, which will further reduce the complexity of the calculation to analyze and process them using the selected base. In this context of UAV motion modeling, this has reduced the computational complexity by up to 13%. Thank you for your attention. Have you a question for my report?